Okay.
Are you ready?
Something like that. Something similar.
Okay. So where are we? EM algorithm for mixtures. We need more light here. So our plan for today is to be a little bit technical to understand the EM algorithm. A little bit more mathematical than last time. So we'll, for 5 minutes here, I'll do a recap of what is it that we want. So what do we have? In 1D, we said there's a mixture, right? So there were two Gaussians. So let's call this normal one or P1 of x. Frequency. So this is P2 of x. This was the normal of a certain mean and certain sigma on x, and this is the other normal. Overall, if we think of a mixture, it's not really like that round. Here one. This is sigma 1. And this here is sigma 2. For a mixture, we have the overall f of x. F of x would be this dotted line. That's the combination of both of them. This is f of x. That is the overall frequency of x. So what that is the sum per components. In this case, I have two components. W, I think we call this WK, PK of x. So that's a mixture because it's a linear combination of few densities. We have the condition sum of WK equal 1. Those are called the mixture coefficients. And for us, in this example, that would be some W1 times the normal 1 of mu1 sigma 1 x plus W2 of the other normal. But that's only two components. I could have 5 components or 10 components. The components are the number of Gaussians. Very important, components or number of components is not the same, this is K, as the number of dimensions, which is typically D or maybe big D or something like that. So I've seen this quite repeatedly. People are confused because why do I have 3 components if my data has 784 features? Okay? Sometimes called features. features have to do with how rich the data representation is. And you're going to see 2 weeks from now, we're going to start playing with these features and say, do we really need 784 of them? Maybe we don't need that many. Maybe we can use less. So that's not related to components. Components have to do with what? What dictates that I have 2 components or 3 components or 5 components?
The number of classes you have?
The number of classes, it's an intuition. You're saying since there are 10 types of images, zeros, 1, 2, 3 digits images, you believe there's 10 classes. But if I don't see the labels, if I only look at the data, I see the images and somehow I can visualize them. That's hard because it's not easy to see 784 dimensions. But if I could, visually, what will look like to tell you, hey, you need 4 components. What do you expect to see to determine the number of components? Partitions, that would be hard notions, right? But in a soft version,
4 different groups.
Groups or densities, right? If you see a lot of data points grouped around one value, right? That's a mean. That's one of those means. You see a group of points grouped all together around the mean. That says you found the mean. Now, if you see another group of points, images or emails or patients, grouped around a different mean, right? Then you have a different component. So if I am to look at, I'd say, the density of where you guys students, not just you, the whole master students population, where people come from all over the world, right? It will be, of course, it is possible that the student comes from anywhere, right? There's no restrictions to say a student cannot come from the most unlikely place on earth, Himalaya mountains. That can happen. But if I look at all the master students, thousands of them, where am I going to see density centers? Where's like a place where a lot of students are coming from? India, in particular, some probably big cities in India, right? There'll be, even in India, some places that are more likely to send students here, like a big city, I don't know, Bombay or something like that. It's not Bombay anymore, right? What is it? Mumbai, that's it. Or Shanghai, right, in China, that's another place that will have a lot of people, And there'll be, even in India or China, some rare places, some mountain or desert where it's unlikely somebody comes from there, but not impossible. I want to emphasize this, not impossible. We do not have 0 probabilities. And moreover than that, we do not like 0 probabilities. We don't want to say in here, no value can ever be at this point, because that's a desert in China, so there's no people coming from there. That may be true. If you look statistically at the past master students, maybe nobody came from that place. We don't want to say mathematically that's 0, like impossible. I don't want to get into details, but every time you talk about statistic, density function probabilities, you want to avoid 0 as much as possible. You don't want to say for sure something is 0, because that's not just untrue, it's hard mathematically to work with those values. So, like as you can see, these are very nice round functions. It so happens that if you look at the formula, these lines never touch the bar here. There is no 0. Even if you go all the way down to the plus infinity or minus infinity, you're not going to find a 0. Okay? So in data, we look for those groups, even if they are soft groups, right? And we say, how many groups do I think I have? The more I see data points grouped towards some value, that's probably a nice idea of a group. All right. So what else did we have last time? We have the idea of membership, right? So we say pi ik is a hidden random variable, right? And people call pi ik like this, or expected of pi ik, which is the same as probability that pi ik is 1. This is a hidden random variable which is 1 if what? Xi belongs to a component or group K, and it's 0 otherwise. These notations means the same thing. For a binary random variable, its expected value is the probability to be 1. That's extremely easy to check because expected value is what?
Is it 1 or 0?
It's a sum over all values times the probability of that value. So what's this sum really quick without writing on the board? What are the possible values? 1 and 0. So it's 1 times the probability of 1 plus 0 times the probability of 0. So that's exactly the probability of being 1. Right? Any binary random variable, its expected value is the probability of being 1. So those three things means the same thing. And this is hidden, meaning we're never going to be able to find the exact value. Membership, say that's membership. You cannot hope to get an exact answer. The reason for that is, I gave you last time the example with CS students versus DS students, and the x-axis was what? Programming skills. Now I'm going to say I have two groups of people. I'm going to come up with a different example. Say there's men and women, right? But I only record here the heights. So this x is height per person. So I have people, I have their heights, how tall they are. I know they're coming from two different groups, but I don't know the group identity. I don't know which person, sometimes you get the data, and the data doesn't have men or women in it, right? So I get the data, I get the heights. I can plot the histogram, is this dotted bar, that's the heights. I know they're coming from two groups. I will never be able to know for sure if a certain height is corresponding to a man or a woman. While it is true that men are taller in general, right? So there's a group of people, probably men, with a certain average of height. Women are a little shorter. It's quite possible to get a short male or a very tall female, right? Even though that's more unlikely. So when I get in my data table a height, 5.5, I'll say that's more likely to be a man, but it could be a woman, right? So in data, you cannot expect to find this value exact. You're never going to know if that data point for sure was a man or a woman. But you can model this probability. So this we can find. We can tell, okay, we believe that's a man or a woman. So what is that? This in here we said is the WK times the probability K of Xi divided by the sum over all K's of WK probability K of Xi. So if you want to look visually at some data point, let's say here, that's my X right here. This part is what? This here has to do with one of the probabilities, right? I have to, and this one here, the other bar, all the way here, is the other probability. So I have this, and I have that. And now, the reason I need a W's is because the overall F is not the sum of those two things, right? Geometrically speaking, if you add this segment, that's the first normal, plus the other segment, you don't get the bar all the way to here. You have to weight those two segments to get that bar. So the sum of them, this, is the big F. So that's WK PK of X divided by F of X. If you want one of them, it's how much was the first Gaussian giving you as a frequency versus how much was the bigger one with those coefficients. Now those W's are fixed, but unknown, right? So the analogy, if for men and women, what would be the W's in common sense English? What W's represent?
Number of
Number of people is all of them.
Proportion.
Proportion of men versus women, right? Which again, is something I don't know, right? I get a data table, I get the heights of everybody, but I wouldn't know which ones are men, which ones are women, nor would I know what's the right proportion. Now, of course, if I have the memberships, if somebody comes and tells me, here's which men and women, I could immediately compute the proportion of men versus women. So we know that relationship, we know who WK should be. Who's WK? Do I have it here somewhere? So that should be the sum over pi ik, right? Divide by n. The sum over all i's. That will give me the count, right? As a proportion, it's how many people are in that category divided by the total, so that's a proportion. Of course, I don't have this, so how do I do it? This is impossible. But how can I actually compute it? I'll do sum of the expected values, right? By n. That's actually a good estimator for WK. That's how you estimate things. Again, if you have these probabilities, you know, for each one of us, say how likely it is. What's the expected value of income this month? Suppose that's a variable, right? We look at all of us, we are, say, 100 people in here. My expectation is a certain amount, certain amount, certain amount, certain amount. If you're gonna compute the expectation of how much money we're gonna have total, you just add up those expectations, which happens to be in here probability of 1, and that's the expected of all income altogether. Expected always distributes linearly over the random variables, right? Now, I want to put here what's that in English. This is the probability that a random picked data point belongs to cluster K. So this WK is the probability that if I pick at random a data point from my table, what's the chance to pick a man or a woman? Now, I've seen there's a place of confusion here, which is what's the difference between pi ik and WK? They both probability of being a man or a woman, right?
Yeah.
So what's the difference? This is the probability to be a man or a woman for a particular I. Okay, what does that mean? How is this different than this? So, in English, we say, well, if you pick a particular data point, this pi k tells you the probability to be man or woman, or group 1 or group 2. This in here, we don't pick a data point. You say, if you pick one at random, what's the chance to pick a man or a woman from my table? But statistically, the difference is a conditional. What's the difference statistically between those two things? In here, I don't know anything. In here, I know what? What? So what do I know if I say I pick a data point? What's in my data? The height, right? The only thing I know about those data points is the height. So if you want to think about conditionally, this is the probability of men, women, independent of the height, like without knowing the height. So this is without knowing xi. Xi, in my case, is the height. Right? And this is the probability given xi. So once I know the height, what's the chance of that height being group 1 or group 2? How many people follow so far? Everybody, right? Good. Now, what else do we have? we have a likelihood function, right? We said that last time. We have a likelihood function. Let me see here. Another thing that we have in this particular case, we know the formulas for these n's, right? We said this last time. Let's find a nice place here to say what's this n for a given mu and a given sigma in a point x. What is that? Did we try to do this last time? Was 1 over 2 pi
Sigma.
d by 2. I'm writing in general in many dimensions and with many components, right? So d is the number of dimensions. What else do I have there? 1 over sigma square root. Then I have an exponential of minus 1/2 x minus mu transpose sigma minus 1 x minus mu n. Okay. So the log likelihood, that's a fundamental notion in all data science. Log likelihood is the probability or likelihood that data, there's many names for this verb. One, informally we call it comes, but you can say corresponds, or you can say fits, or there's many others that you can put. The model. Model is given, of course, by the parameters. In our case, our model is 2 Gaussians with a mixture. So what are the parameters? The 2 mu's, the 2 sigmas, and the w's. So the model in our case for a mixture is, so for a Gaussian mixture, this model is a bunch of mu's, a bunch of sigmas, and a bunch of w's. Those are the parameters if I use Gaussian mixtures. But different functions, probabilities, models will have different parameters, right? So when you talk about likelihood, you ask, what's the chance that once I have a model, the data that I observe can come from that model? So here's, and you take the log of it, because without log it's both computationally ineffective, but also unstable in terms of precision. When you multiply probabilities, you get extremely close to 0 numbers. By taking the logs, you make that far more easy to represent. Computers only have so many bytes to represent floating numbers, right? So let's write the likelihood for this case. We have, so there's a product for all data points of the probability, I think that is f of x. But if I take the log, I'm going to get the sum over all data points, sum over all components, pi ik let's see if we can figure this out, times log of xi, log of p of xi, so that's in a normal. I just wrote down from a piece of paper. Oh, hey, you have to figure out if it's correct or not. Where is this coming from? Remember, I take a log, right? So what I want to do is a product of all fx's. Who's f? F is a mixture model, right? So f is this guy here, right? So I want to take the log of the product of this product for all data points. I is the data points index, k is the component index, okay? So this is going to happen in a lot of data problems. Somebody's going to say, here's a likelihood. Likelihood makes sense in many, many ways. Likelihood is a very nice concept. First, it serves as an objective, right? Right? What do you want this likelihood to be when you know your model is good? When the likelihood function is high. The higher it is, because it's a product of probabilities, right? The higher it is, the more means the data you have fit the model that you have. Independent of the model. In this case, the model is a bunch of Gaussians with a combination between them. But even if you have a regression, or a boosting model, or a support vector machine model, or a neural network model, whatever you have, the more you increase the likelihood, the more means the data start fitting that model. Okay? So that's nice. The second thing nice about it, why is it a product? So I have these data points, right? Say patients in a hospital, students in a class, documents from the web, images, whatever. Why do I say I want all f's to be high? Because a high f means that point somehow is likely to show up given my model. Why don't I sum them? Why product them?
Yeah, it's we are finding the intersection and all of them are independent of each other. We are trying to find the intersection of all the points happening, and then we are trying to, because all of the records that we have are independent, we multiply them.
Okay, he didn't say it right, but he meant it right. He had it right in his head, just didn't come out that well. He's saying, why a product? We interpret f's as probability, right? Keep in mind that we spent quite a lot of effort to make sure f is a density function. Remember last time we were saying we want f to be a density function, even if it's a formula of many densities inside, right? Because it's a probability, we want to really interpret f as the chance to observe this patient. Assuming my parameters are right, what's the chance to observe such a patient, such a web page, such an image, such a document, such a text email, whatever we have, right? Now, why is a product? So what he's saying is because I think of data points as being independent. Is that really true? Are data points independent? I mean, I'm not asking exact. It's never going to be perfectly true. But does it make sense to say, so I want to make a comparison. What I mean by say data points are independent versus what I mean when I say features are independent. Features are the attributes, right? So suppose for a person, I have height. That's the one I'm using here. But I may have also weight, name, race, income, age, all kinds of properties of people. I'm only using one, but I could use two, right? These Gaussians could be two-dimensional. In fact, that's why I put the big sigma, because I want this to be multi-dimensional sigma. If I look at heights and weights of a person, are they likely to be correlated or not correlated? Is it likely that taller people have more weight? Of course it is. Right? Many features will be correlated. In fact, we struggle a lot in machine learning to find uncorrelated features. It's a big deal, finding the uncorrelated features. So it makes sense because however nature makes people or documents or images, whatever I extract from them comes from the same image, therefore it's likely to be correlated. So in the feature sense, it's not unsurprising, I think, that features or some features are correlated. How about in the data point sense? How do I think of these data points? Students, or web pages, or images? Do I have a generative process in mind? How did I end up with 70,000 digit images? How did that happen? How do you think it happened? Where the 70,000 images came from? Speculation is good.
They look kind of similar. Like some of them were quite similar to each other.
So first of all, I think we all can agree that a lot of real data sets, that's our main job for the class, even though in some homework you're going to have a non-real data set, were actually real. They were not generated by me in MATLAB, pixel by pixel, right? Those images were actually existing in reality. So where do they come from, these digits?
Connected.
From where?
Added in documents.
From us.
Huh?
Just from the post office.
Right. So people were writing digits, a zip code, right? And the post office thought at some point, hey, we could probably invent some scanner machine, very simple. That was many years ago. That will just read the digits as you write them and know what the digits are. So we don't have a person reading those digits, plugging into a machine. They didn't have computers back then, maybe, right? So they came up with that. And now, since they scan every single digit on 20, what is it? A 6 by 26 or something like that, right? 28 by 28. Then they collected those images. So images happen. Now, are they likely to be independent of each other? If everybody who writes a zip code writes how many digits? 5 digits. But I don't, even though I collect them 5 at once, I put them together all, I don't put them together 5 groups that appear in the zip code. I put ones together, 2 together. They may come from different zip codes, right? Is it likely that a 2 written by me when I send a letter to somewhere be somehow related to a 1 written by him when he sends a package to his mom? No. The different writing styles, different destinations, different papers, different, right? There's no immediate reason for similarity in there, right? How about the collection? Is the collection biased somehow? Because sometimes when we collect data, maybe the data is independent as a whole, like all the digits, but when we collect them, we have a bias. We only collect the ones dependent. This is a subtle thing that most people don't even realize they have a bias. The trivial example of this is, I want to know who's going to win the election, right? So I start asking only people in California, right? Then that prediction won't reflect who wins the election. I have an obvious bias. I'm only asking people in California, right? But it's unlikely that those images from the stamps came with a bias, right? Maybe there was a selection, some digits were unreadable, so we exclude those. Would that produce a bias? Maybe a small bias, maybe a 3 is more unreadable than a 6 in general, but I think we can agree that the collection was roughly independent. How about patients? If I go to a hospital, I have some problem, and he goes to the hospital, he has a different problem. Are we likely to be correlated somehow, other than having some problem? No. Now, it is true that if people have the same problem, they should have the same features, right? That's okay. That's why features are representative of whatever we want to do with them. So this product comes from the natural independence of data points. You should ask yourself the question when you deal with a data set, is it likely to be independent or not? Most of the time it is. The typical situation when it's not independent is when, say, I use a computer log. I try to detect some. There's many entries in a computer log. I look for some. And as soon as I see something, I collect more data. Right? Suppose, if I see that I have a problem, I'm going to investigate my family too, medical problem, right? Then it's likely to obtain correlations. If for every data point that have a property, I collect more data points because that data point has a property, then all the data points collected are likely now to be correlated with that one that I started with, right? So in a log database, that's sometimes a problem. People look for anomalies. Difficult to define what exactly is an anomaly. But when they see some problem, typically there's a security flag. There's more information popping up then, and more logs being processed. But that's because the first time I've seen the flag being on. So now my data is not really independent. What if I found something interesting in a Wikipedia page, and because that's interesting, I crawl the pages from there. Now those pages are not independent with the one I started because they have the outgoing links to those pages. It's not like I can claim once I crawl from a page, the neighbors based on some criteria, the pages I've got are a random subset of pages from the internet. They are not. They crawl because I found something interesting in the first page and I went from there. Okay, so with that discussion, let's see the formula. Can anybody tell me why this is coming from, if I take the log of product of this, right? P is this normal, right? Why is pi k coming up here? So this is what I didn't say. This is the expected over the log with respect to pi I k membership. The reason I have to use expectation is because I don't know for a point if it's a man or a woman. But I could say with some probability is a man, and some other probability is a woman. Every function can be computed in expectation, aka an average over the possibilities that all of us could be men and women. We don't know that, but we know the heights. So then this expectation induces these pi k probabilities. How about the log of wk? Where is this coming from? When I take the log of this, I'm going to get the log of wk, but what happens to the log of a sum? Is that true? Not really. Log of a sum is not the sum of the logs. Right? Log of the product, it's a sum over log. So that the log of the product becomes a sum. But what about the log of f's? Why is that? So I think everybody can see that the log will eventually transmit itself to this pi and p, and p is the normal, so then I get log of the normal here, right? But what happened to the log of a sum? That's, by the way, you should know, that's a well-known problem in machine learning. Log of a product, it's easy. Every time people see put products, even if they don't need them, as soon as you see a product that has no place to be, you should know this person wants to take a log. That's why they put a product in, because they like to take the log and they know the product goes hand in hand with the log. Unfortunately, mixtures have a sum. Taking the log of a sum is not easy. So what's going on here? It's an approximation. It's that thing. Log of a sum is the sum of the logs. But it's a little bit more than an approximation. How is the log of a sum versus the sum of the logs? If I look at log of, say, sum of some variables, say z psi or whatever, x size. I don't want to say x, I want to say y. How is this compared to the sum of the log of y i's? But if I want to, okay, I know they're not equal, right? Can I say something about?
The values are extremely small.
If the values are what? So they're definitely not equal. The problem is I can't deal with log of a sum. If I put a log of a sum here, the whole derivation goes to like trash. So I can't do that. So I really like the sum of logs, obviously. They're not equal, but what can I say? This is a good moment to recap something important for all mathematics in data science. What does it mean for a function to be convex? How many people know that, convex? When do we say f is convex? Second derivative is positive. Or f of an average, any average, doesn't have to be 2. Sum of, what did we say there, yi, f of yi divided by how many there are, is, in a convex function, if you look at the average of values, this, and that, versus the average f. Here's the average f, here's the average of the values. It's easier to see with two things. So suppose I have y1, y2, this is y1 plus y2 by 2. How is this average of f? This is f of the average, versus I take f of this, and average those.
Should line the convex curve.
Huh?
Should line the convex curve. All the points done.
No, that's not it. I'm just asking for something very simple, 5th grade here. I took two values, I compute the f in f of them. This is f of y1, this is f of y2. But I can compute f of this in here, if f of y1 plus y2 divided by 2, right? How is this f of the average compared to the average? This in here is f of y1 plus f of y2 divided by 2, right? Which one's bigger?
Average of.
F of the average is smaller, average of f is bigger. You should be able to prove that from this. If the second derivative is positive, f of the average, sum of yi divided by n, is smaller than sum of f of yi divided by n. So that is equivalent to say the second derivative is positive. It's a good high school exercise for calculus, this one. Okay, how about concave? Some people call it anti-convex. It's the opposite. If a function looks this way, here's y1, here's y2, here's y1 plus y2 by 2. Here's the f of the average. And here's the average of f's. So if a function is the other way, the derivative is negative, right? And f of the average, y1 plus y2 by 2, is bigger than f of y1 plus f of y2 by 2. Okay? Sounds good. So what about the logarithm? How does the logarithm look like? Concave or convex? Concave, definitely, right? So what can we say? We all know the logarithm looks like that. I mean, it doesn't, it goes to infinity still, but it's, that's the logarithm, right? Definitely curves this way. So logarithm is in this category. So then what do we have between those two things? What's the right relationship we want? If we take the average of those, we get, and we apply the logarithm, we get a bigger or smaller value than if we take the logarithms and we average them. Which one's bigger? That's because logarithm is concave. Okay, nice. This is something you should know about logarithm and about convexity. So which one I should have had? Which one of the two is the one that I had? This one is the one I had, but I ended up with this because math is easier. So if I increase the likelihood, that's my job here, right? In our machine learning algorithm, we want to increase the likelihood. which one we actually increasing after I make the approximation. We are increasing this one. And the theory goes, the story goes, if this is increased, at least it provides a lower bound for the real one. Right? The other way wouldn't be nice, because if we increase one, there's no guarantee to increase the smaller one. But if we increase the smaller one, the true one, this is the lower bound. So this is the true likelihood. And this is the approximately. Say lower bound. Like. Yes.
So what does those two become?
Hmm?
What do those two, like, what does that inequality become?
All these are equality when the y's are the same. Has to do also with the inequality of the averages. Inequality of the averages, the square average bigger than arithmetic average, bigger than geometric average, bigger than harmonic average, could be explained with convexity. Right? That's another thing you should know. They always equal the same average when the numbers you average are equal, because then if the numbers y1 and y2 are equal, of course the three f's, f of y1, f of the average of y2 are the same number, so then they all equal. Okay, well that's not critical for us. It's just I'm giving you a background here. When you hear of likelihood, and if you look at the math and you see, okay, there was a logarithm of sums, but now it's a sum of logarithms. It's definitely because the mathematics is a lot easier with the sum of logarithms. And what happens in reality, if we try to increase this, typically it's a lower bound of the real thing. Now, say you guys believe me. What do I want to do here? Remember we have these M steps and E steps. So where did this come from? Let's see first of all what were they? So when we did M step, we said what? What was given? What we're trying to compute? I'm now in a soft version. So what do I have in an M step? I have the memberships, no? So given pi I k, memberships are soft. I will never have 0 or 1 values, right? I will never be able to tell this data point is certainly a man. But I'll have a probability. I think, 30% chance is a man and 70% chance is a woman. So I have these are memberships, soft memberships. What am I trying to compute? I'm trying to compute mu's, right? Who did we say mu is? You guys remember from last time? Sum over all the data points. What was mu? How do I average things if everybody has a weight? Everybody has a probability to be in the basketball team. How do I compute the center of the basketball team or the mean of the basketball team? I do pi I k, right? That's the weight of every data point to be in the team times the data point, just like in k-means, it's an average, right? Divided by sum of the weights. This is a weighted average. Okay, and then what about sigma? Sigma k will be, let me actually write it down separately. Where? Here. Let's write it. I'm going to erase this in the video now. Here. Sigma k is sum of pi I k xi minus mu is a vector times xi minus mu k transpose. So it's a sum of those things divided by sum of pi k. And this is the covariance matrix for component. Okay. What I would like to do today, but I'm not sure we have the time, at least to start, you guys will finish. That makes a lot of sense, right? Isn't that just a natural continuation from k-means? In k-means, we average the points and we divide by the count, right? Because that's why we get an average. And your homework 2, exercise 1, which you haven't seen yet, is to prove that that minimizes the k-means objective. We want to do the same in here. It's a little bit more difficult. What I want to say is this is not just a nice intuitive mathematics. It actually can be demonstrated is the right formula. So what I want to say, this is my objective here. Assuming the pi k's are fixed, because that's my assumption, pi's are fixed. How can I show that the best way to do the mu's is this formula? What would I have to do mathematically? So if I give you this exercise, I want to maximize this thing. That's after the approximation. Pi's are fixed. There's some coefficients that are not changing. How do you know which mu's are the best ones to optimize, maximize this formula here?
One which has many data points around it.
What?
One which has many data points around it. Similarity with others is
I'm asking a pure mathematical question. If you want to maximize this function, pi's are not moving, pi's are fixed. How do I know what are the right mu's? Huh? I have to take the differential, right? I take the differential of this, and hopefully, once I have the differential, what do? How do I find the mu's? Make it equal to 0, hoping that the 0 corresponds to the maximum, right? That's the poor mathematician's hope, like, okay, if I make it 0, it's what I want. But real mathematicians check other conditions to make sure that 0 corresponds to what they want, right? We're not real mathematicians, so we're just gonna get equal 0 and see what happens. Right? So how do we take the differential to this? How does that look like? A differential with respect to what? Because these are fixed, but there's more variables here. There's mu k's, sigma k's, and w k's. So if I care about the mu's, I take the differential with respect to the mu's, right? So let's see if we have any success here with that. Here's what this is saying. Differential of the logarithm of blah, blah, blah. That's the objective function, the likelihood. With respect to mu k is the differential of logarithm of 1 over 2 pi d by 2 sigma k square root here exponential of minus 1/2 xi minus mu k So this is the likelihood, I think, of f of xi, just for one of them. The reason I'm doing for 1 is I could sum them up maybe later on. So I'm differentiating for 1 with respect to k. So I have this logarithm here, right? I hope I got everything right. With respect to mu k. So exponential of this whole thing. That's easy to see. Let's see the next one. 1/2 differential with respect to mu k of xi minus mu k transpose sigma at minus 1 k xi minus. Why is this equal to that? So what happened here? Let's do the easy part first. The log of this exponential is it, right? So that's fine. And then we need some linear algebra skills in here, not just derivatives, I'm afraid. So why is this true? It's okay to spend 5 minutes trying to figure out. I should say this is completely optional. I'm not going to ask such a question, nor I'm expecting you to know this at the end. I just want to, since I'm here, I think I figured spending 5 minutes getting you guys familiar with how likelihood works and how people think about those things makes sense, even though you may not be able to do this math on your own. That's fine. That's clearly a PhD level. But let's take 5 minutes just to see, can we figure out where this is coming from with some approximations. So one thing is clear, logarithm of this times that, right? It will be logarithm of this plus logarithm of that. And now logarithm of an exponential is that, what's inside, right? So that's pretty much written there. I think I missed the minus 1/2 here. But what happened to the rest? Is the logarithm of this part, right? Why is it 0? There is no mu there. But what happened to the derivative when I do the log of exponential? The derivative still applies, right? So I didn't lose the derivative here. Derivative of, okay, good. And here's another thing. So saying this is xi minus mu. This is something we won't be able to figure out. So there is a formula that I'm going to give it to you, but I won't expect you guys to know it. It has to do with matrix derivatives. Differential of x transpose AX with respect to x is a vector here, is x transpose A plus A transpose. So that's a formula. We're not going to prove it. But for people who want to do math, there's something called matrix derivatives, and then you can obtain this formula. What I would like instead to do is to kind of find some analogy explanation why the differential of this is this from differentials you know. Now that's a story, it's not a mathematical argument, but sometimes a story serves better as an explanation than some formula I cannot prove. Now if you want to prove it, you need matrix differentials and you have to deal with that. This is an expression, derives at a vector, it gives you a vector. So how would this look in 1D? If I only have one dimension, those are not vectors now, right? Because everybody has d dimensions here. X has d dimension, mu has d dimensions, sigma is d by d matrix. what happens in 1D? If I only have this in 1D, minus 1/2, how would it look? X minus mu, right? Transpose is not necessary in 1D because transpose of a number is a number, times sigma is a value, right? Times x minus mu, right? And I want the differential of this whole thing with respect to mu.
Should be inverse.
What?
Sigma square should be
So if you take this differential, it's a degree 2 polynomial in mu, right?
Yes.
So what's the answer?
X minus mu by sigma square.
I think it's
mu one.
pretty much that, isn't that? Isn't this x minus mu times 1 over sigma squared? 1D, so now everybody's a real number. X is a real number, mu is a real number, t is a real number. Is that correct?
Yes.
So that's not a mathematical argument. It's not because it's 1D, can I make all the symbols be multidimensional and the whole formula holds? No. That's not a mathematical. I'm saying intuitively, it makes sense that if that holds in 1D, the whole thing holds in many D. Now to prove that rigorously, you need matrix differentials. So that's no big deal. Matrix differential, somebody who's been good in high school at calculus will figure them out in a few hours. So if you want to spend that time, I can give you some notes for it. You can read also these notes. What I want you to understand is the intuition that the derivative follows the same principle as in 1D, which I'm sure you can do it by hand and get the answer. Okay. So let's assume this is true. Now, that was the differential of 1f. So I actually need the differential of what? The sum of all f's, right? I did the differential for 1f, but might include the sum over all f's, right? So now, what is that? Differential of the sum of all f's with respect to mu k. The sum is going to distribute over the differential, right? Differential of a sum is the sum of differentials. So I'm going to get sum. Don't be confused between the sum and sigma. This is the sum over I of x minus so I'm going to have it here. I think we made a mistake somewhere, but let's see. xi minus mu. Okay, so this differential of that transpose sigma k minus one. What we need to add here, I think we made a mistake, so we'll put it here. This is the pi ik probability. So why is it that I have a pi ik that somehow it's not in here? The mistake is in here. If I use fxi like that, I have the pi ik, right? So this in here is not correct because it cannot be correct. fxi must include somewhere pi ik. And in here, there is no pi ik. So we can explain this in two ways. The easy explanation is this is a differential if pi ik is 1. It's kind of a conditional differential. Or we could have done it literally with the probability of pi ik being 1 times this, plus the probability of pi k being 0 times when it's 0. But that's 0 anyway. So when I compute the expected value, I'm going to get the probability of pi k being 1 in the formula here. I I think this is something that some of you will not be able to follow that well, I'm afraid. So I made a mistake here. When I computed this, I didn't include the pi k, because this is only when pi k is 1. Now if I compute the real function that has an expectation over pi k is 1 or 0, I'm going to get that probability inside. So now finally, if I set the differential of the sum of fxi's to 0, I'm going to get that. How does this work? The sigma doesn't do anything in here. It's a constant. So I'm going to get the sum of pi ik expected values of xi minus mu k has to be 0. Right? Because this is a matrix, it's a fixed matrix, right? So the differential is not with respect to that one. That's a constant here. So this part has to be 0. Now, does that mean what I want? In here, can I rewrite mathematically this to get exactly this here? Let's see. This I can write as sum of pi ik times xi, this is sum over I, is sum of pi ik times mu k common factor, because mu k is the same for all i's. So now if I divide the sum of pi k, I get this updatable. How many people follow me? No? Okay, where are we stuck? Let's see. Do we understand this log likelihood? But we made a mistake the first time. This is only for pi k equal 1. Ignoring that, do we get from here to here? From here to here?
Yeah, but when we say m step, we say this is a software membership, so pi k should be a probability, it should not be equal to 1.
Right. We don't know if it's 1 or 0. So we're saying with probability that pi k is 1, we get this likelihood. There's another probability of pi k being 0. Now we don't have to compute it because it's 0 times that, right?
So here there's only two membership, 1 or 0.
Yeah, but you don't know them. You don't know which one is it. So the only thing you can get is an expected value or probability to be one or the other. But let's try to figure out the math a little bit. Did we get here? From here to here? That's the stuff that I told you need linear algebra, but if you don't, you just do the one from 1D and you cross your fingers that it might work in many D. Right? So we got here. Now, what I did here, when I do the sum, I included this part of the sum is the same like the one in here. What I have is the probability of pi k to account for the fact that pi k might be 1 or 0. Hands up, who's with me? At least the story seems believable. Like Santa Claus and stuff. Like it's not Santa Claus, right? It's something that may have a chance of being correct. No? Let's ask some questions then. Like what year did you question the Santa Claus story? Some people go over there like 25 and they still. At some point you start saying, you're not gullible anymore, and you say like, this doesn't seem realistic to me, right? Do you feel like that? Like this is not realistic, or we feel like there's a good chance to be realistic?
Is this for hard threshold or soft threshold?
Soft.
So, but if it is soft, then for pi k is like we have a 1 0.
Okay, you stuck at how this pi k equal 1. Okay, I'll get to that. But assuming we get over that, do the math works out mechanically? Do we get from here to here? Do you see this is that sum? And if I make it equal 0, I get the pi's out, the sigma out, because sigma is a constant, and I get my formula. We at least follow mechanically how the math works out here. Yes? No?
I might be wrong, but I think you're missing a log there.
Okay. Where? Here?
Now after that?
Here?
Yeah, right.
This is simply saying if the differential for one xi is this, the differential from a sum of fxi's is the sum of this.
Right, but we use a log there. We're not getting the log.
Yeah, but a log was, oh, you're right. This is the sum of logs. Right. So logs I'm taking all the time of the likelihood. I will never have a likelihood without a log in it. So f is a likelihood is log of f. In fact, sometimes f is included in the, sometimes people call f the log directly. So it's not log of f, f includes the log. But the observation is correct. This was log of f, I have a sum of log of f's here. But then I just have to sum up these formulas, right? And when I sum them up, if you pay attention to the mathematics, this goes away, and I get sum of pi's xi equals sum of pi's mu k. Mu k is a common factor, so mu k will be sum of pi I k xi divided by the sum of pi k. That's the equation right there. Still not convinced?
Where did the mu k go again?
Okay, do we buy this? Because I brought this minus into the left side and the right side,
Okay.
right? And I common factor mu k on the right side times the sum. Now if I really want mu k, I have to divide the whole left side by this sum of pi's, and I get that formula there. Hands up. Who feels better now? Still not many hands. Okay, more questions? I'm not expecting you guys to take matrix derivatives, okay? Let me be clear about that. But what I'm expecting, if somebody presents such a derivation, to have at least a clue where it's coming from. You have to take a machine learning class and probably do a PhD to be able to do those things on your own. Okay, you have a new objective in its derivatives and all that. Yeah, we're not there yet, but at least we have to have a sense of where is this coming from. Your homework problem essentially asks you to prove this in a hard case, much easier, not in the soft case. Because in the hard case, this is the sum of xi's with membership equal 1 divided by how many there are. Yes?
Yeah, Professor, why do we need like expected value of pi I k again? With that, like,
Where is it coming from, or why do we need it?
or why do we need?
So this is coming from, is the same question like he asked a second ago, and I say postpone it. It comes from the fact that this likelihood is computed conditional of pi k equal 1. But that's only one part of the story.
Yeah. No, I mean, I'm confused about like the one, not this. You say that we don't know pi I k, so that is why we.
So pi k is a hidden random variable, which is either 1 or 0. We know everybody is a man or a woman. But by the table we've got, the data we've got with heights, we don't know if it's 1 or 0 because we only see the height. What we can compute is the probability of being a man or a woman. So I may see a height, 5.5 feet, 4 inches or something like that. I'm saying, I think with the probability 60%, this person is a man. And 40% is a woman. Right? So that, as I said here, is exactly the expected value of the random variable because it's binary. The probability of being 1 is the same as the expected value. So whether you talk about probability of being 1 or you talk about expected value, that's the same exact number. So we can compute those expectations or soft memberships. It's soft because it's 60% chance to be part of that category. In reality, we're never going to know for sure. Unless somebody comes and fills the data column that's missing, man, woman, man, woman, man, woman, we're never going to know if a certain height. Because even though it's 60-40, there could be men of that height, there could be women on that height. So we're not going to know for sure if that height is a man or woman, no matter what we do. But we can compute a probability. So pi k in brackets is the probability.
My question I want to go back to this one. When we computed the log
Why do we look at the expected value of the log n?
The same thing, right? It's expected over whether there's a men or women. If I tell you everybody is a man or a woman, you can compute a direct likelihood. But you have an expectation over everybody having a probability of being man or woman. So think about it this way. I'm only talking about 3 people here. There are 8 possibilities. Men, 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 woman, 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 man, man, so on and so forth, right? Each one of them has a probability. Because I have a 70, 30, 60, 40, 50, 50. So there's a certain probability of getting every configuration. So the likelihood is 8 likelihoods with certain probabilities, whether those are men and women. Expected value over all these probabilities is the expected likelihood. Yes?
So the membership over there, can it be said that that's like for one particular f of x?
Yeah, but it's still conditional on something. That's like the same when we say conditional of another random variable. If you ever saw this, probability, I think that's what you guys have stuck. Probability of x given y equal 1. That doesn't mean y is 1. Right? When somebody writes a conditional probability, they don't tell you y is 1. They tell you in the case of y being 1, this might happen. But it doesn't mean y is 1 for sure. Same thing in here. Y is still a random variable, right? Same thing. Pi ik here is still a random variable, but in the case when it's 1, I get this likelihood. And then if I compute the expected likelihood will be times the probability of being 1, right? Which is the pi k in these fancy brackets. Yes?
Is this related to the latent variable?
I think so, but that name I think is a little vague. I think many people use that name for many things. But yeah, all those latent variable models will, I think, have a likelihood and have some optimizations methods built in. I would have to, you have to give me exactly some formula definition to say if it is. But I think a lot of generative models with probabilities work this way. I come up with a likelihood based on my models, and then I try to optimize my parameters, in this case mu, sigmas, whatever, so that data fits better the model. So EM does that. It finds you the parameters so that the likelihood increases. Now why EM, why is necessary, why it's 2-stage? Because I can't find the parameters without memberships, and I can't find the memberships, chicken and egg problem. That's why I need to alternate, right? Now, of course, we only did step number 1, the baby step. There are some other steps here, right? There is this. Wow, how did I get to this formula? I won't have time to do it, but how do I get to it? If I want to do the same, what do I have to do? Take derivatives with respect to sigma, not mu. And then there is another step. This. WK, how would I do this? What would I have to do to get the WKs out? Take the derivatives with respect to WK. That's a little tricky. Let me take 1 more minute. I'm kind of squeezed with time here to explain why it's tricky. Mu's and sigma work that way. Now, it may be complicated, but the basic principle is very simple. Take the derivative, make the derivative equal 0, right?
Yes.
And that's going to give you the mu's and sigma that maximize the likelihood.
Yes.
Why is it different for W's? Why for W's I can't just do that? Take the derivative, figure out the W's that make the derivative equal 0. There is something else with W's that I need to account for. They are. So W's are parameters just like mu's and sigma. But why can't I do exactly this for W's? So for sigma, I will take the derivative of the sum of logs of f of x to the derivative of sigma k equals 0. It's going to give me this formula. assuming I know matrix derivatives, assuming I can do the math. Why can't I do the same for W's? So for W's, the plan would be to do what? Take the derivative of the sum of logs, right? With respect to WK and make it 0, right? And that should give me the formula. There is something with W's that will not allow me to do that exactly that way. What is it?
We don't know the pi case for.
No, I'm in M steps, so I know I have some pi case already. So I'm assuming I have pi case. Why is W different than mu's and sigmas?
We have constraint.
We have a constraint, very good. There is a constraint. How do I say I want the maximum of something subject to this constraint? Can't just take the derivative, right? Take the derivative, I get some W's, they won't satisfy this constraint. Right? Can I say, take the derivative, get some W's that maximize your sum by setting the derivative to 0, but then normalize them? Would that be okay? To find the W's this way, but then say, okay, they don't sum to 1, so now make them sum to 1? No, that's no good. There are probably some other constraints here, they have to be positive. So how do you do that mathematically? You guys know to set up a derivative equals 0, that gives you the maximum of a function that's concave, right? So maximum. It's going to give you 0 minimum if it's that. But how do you do the same optimization when you have a constraint? Huh? There is a mathematical similar methodology that does it with constraints. That's it. Lagrangian multipliers. Now, we don't have time to explain Lagrangian multipliers, but it's a mathematical technique that does exactly that. It says, how do you find the maximum of a function subject to a constraint? The principle of it is I take the maximum, so the maximum is here. If I take the derivatives that are constrained, I'll get this point. These are the circles that have the same value. So this is all equal to 1, 2, 3, 4, the maximum is 10. But I take now the constraint, and I say, I can't go to this point, the maximum, because it doesn't satisfy the constraint. I have to take the biggest value that touches my constraint geometrically. So the Lagrangian multiplier will say the biggest you can do is here. It's not the unconstrained maximum. It's the constrained maximum, because if you go more towards the maximum, you don't satisfy the constraint. If you go on the other side, you satisfy the constraint, but it's not the maximum we can get. So Lagrangian multipliers work by finding the tangent of the constraint to the maximum function. Now once you understand that, the math is not very hard.
So kind of in regularization we do similar stuff where we say the constraint on W's and we penalize W's that are high, as in case of mentioning.
That it's a heuristic, won't give the maximum. So the right way to do the maximum is to take the objective, add a constraint term to it, then take the derivatives. That's how Lagrangian multipliers work. It's something that we expect you to have seen in college. Not exact, but we think minimizing a function without constraints is a high school thing. People take derivatives equal 0, get the value. Minimizing or maximize the constraint, it's a college thing. So if you took a course in calculus in college, you should have seen Lagrangian multipliers. Now, it won't be necessary for this class. I just want to give you a heads up that for W case, we need Lagrangian multipliers because of the constraint. Let me move on, because I need to say more things here. Okay, so that's the E step, right? That's the M step. We also have the E step, which is given what? Mu's, sigmas, and W's, right? Compute optimal pi ik, it's in brackets. Again, because I will never be able to compute 0, 1 pi I k, but I can compute the probability. So how do I do that? We have a formula somewhere here. It's this, right? If I have all the parameters for every data point, I can say, okay, what proportion each is Gaussian out of the total, divide that proportion by the function, I get that. But there's still a mathematical thing that needs to be proven, just like we try to do here. This is common sense intuition. The question is, can you argue that this formula is the maximum you can get, assuming the mu, sigmas, and w's are fixed? So these proofs are in those notes, which I'm going to put online. They're not required for the class. I'm not going to ask you about them, but if you are mathematically talented and you have time, you would have to prove similarly here that this formula realizes the maximum given the stuff. You have, as a requirement, your homework asks you to do this in a hard case, which is very easy in a hard case. If you don't assign the point to the closest center, it's a closer center than that one, you can immediately increase the objective by changing to the other center. But in here, you need to take some derivatives to make it work. Okay. So with that being said, I would like to, so that's probably the most mathematical lecture we have the whole term, okay? Okay, I know it's a little, okay, I didn't expect that, right? Did you? You didn't. But once you get to it, you can say, okay, the worst has passed, right? I would like to talk about two examples if I have time in 9 minutes. One is the height and weight. I'll show you that on the computer running EM. The other one is a slight variation of EM for a different purpose. Just to show you that this principle of chicken and eggs is quite general and it can be applied in many ways. So here is this setup. I have k coins with different biases. Biases, of course, of a coin is k coins, q1, q2, qk. Of course, qi is the probability of getting a head. If I flip a coin, those coins are not all fair coins, so it's not 50-50. Right? I have wk mixture coefficients. That is the probability of selecting coin I. Okay. So the principle goes, you pick a coin, right? One of those k coins. You don't know the bias of the coin. You start flipping it. You flip the coin n times. That results in xi being xi1, xi2, up to xin. All these are head or tails, right? So I pick a coin, I flip it n times. You can think of n equal 10. Now, I pick another coin, so it's a loop here. Pick a coin, flip it n times, you get that. So I get x1, x2, x3. So this would be x3, 1 up to x3, and what happens here? Every time I pick a coin and I flip it a number of times, so that's consistent. All the flips happen to the coin I selected. For some, I'll notice a proportion of heads different than other flips, right? So in here, I may have 3 out of 10 heads. Here I may have 5 out of 10 heads. In here I may have 6 out of 10 heads, 9 out of 10 heads, 3 out of 10 heads, right? Number of proportion of heads. You guys see this how it happens? So I pick a coin, flip it a bunch of times, 10 times, and it's fixed. Record how many heads I've seen. And now I do this many times. The question is, can you figure out the W's? What was the chance of picking each coin? And the biases? So the task in here, find from data most likely W's and Q's. So your exercise is figure out how would you apply EM to solve this problem. It's very similar to what we've done, but you have to think in that context. I have this data, but every flip could have from any coin, right? Even does a coin have a bias 50-50, when I flip it 10 times, I can get 6 heads, right? Or I can get 3 heads. There's no guarantee that if I get 3 heads, that the bias of that coin has to be exactly 3 out of 10, right? For any coin, there's certain probability to get a number of heads. So we cannot tell for sure what coin has been selected, just like we couldn't tell what height corresponds to man and woman for sure. Every one of these 10 flips could have come from any of the coins. But if we somehow manage to get a model for the data, maybe we can figure out what are the biases and what are the selection probabilities. Do you think I can show you something really quick on the computer here? Do you still have that dongle? I think I have one, but it doesn't work very well. 1 minute. So here's the run that you're gonna have to run EM twice. One as a package for real data because it's hard, and one as a implementation of your own for toy data because that's very easy. So the data you're gonna have, it's gonna be generated to fit Gaussian perfectly. So if you look at this picture here, if I give this data, this is a 2D, so data has 2 dimensions. It's also 2 components. You can tell this has been generated specifically to fit a Gaussian mixture. Look at those nice grouping here. In reality, if you take images or documents, you're not gonna see such a thing, right? So for this data, which we give it to you, you have to write EM yourself. But we allow you to use sigmas and mu's and all that from your programming language. So you don't have to compute a normal distribution. But the main EM loop has to be written by you. For real data, there's a problem with that covariance matrix, and it's hard to implement, so you're gonna use scikit-learn or something else to run. So what's gonna happen when I start? I initialize it somehow, and now I'm running EM, E step, M step, E step, M step, right? I should notice that while the data points don't change, the Gaussian change until they get to a stable position. So if you want to debug your algorithm, if you want, you may want to see something like this, not necessarily as a plot, but how my EM changes. So because it's a very nice data set, you can't go wrong with this. No matter how initialized, it's going to go to the right spot. You want to see from iteration to iteration, okay, what happened? Just like in k-means, when I show you two times ago, how those centers become more globular, in here you should see that one Gaussian becomes wider because it fits more wide distribution of points. One becomes more straight because it's more dense points in here. The means, the mu's, you should see that the mu's kind of slowly converge to the center of the green and the center of the red. And that's an indication that the EM is doing the right thing. The proportion, you should also verify, okay, the W's between them should be roughly the proportion of reds versus greens. So while you're doing it for a toy data set, you'll be able to implement your own EM and verify it and demo to the TA. For real data sets, you won't be able to do this unless you spend like a term project on it. That will make a term project, implementing EM for a real data set, because there's problem with scalability. So next time, we'll give you some demos on real data of EM. And before then, hopefully, we'll have the rest of the homework in place. There is a thing here. I think we have to move quickly.